Tonight, we're going to explore something that sounds like science fiction, but is pure physics. Imagine you're deep inside the atmosphere of Jupiter, not orbiting it, not flying past it, inside it. You want to leave. You want to escape. But here's the problem. There is no ground beneath you. There are no launch pads. There is no surface to push off from. Instead, there is only gas becoming thicker and heavier in every direction below you, pressing inward with a force that would crush a nuclear submarine like a paper cup. The deeper you are, the worse it gets. And Jupiter's gravity, the most powerful of any planet in our solar system, is pulling you down into all of it. This is not a place that lets you leave. This is a place that swallows you. Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already understand. Gravity. You feel it right now. It's holding you in your chair. It's keeping your feet on the floor. It's keeping the atmosphere wrapped around the Earth like a blanket. Every time you jump, gravity pulls you back down. Every time you throw a ball into the air, gravity curves its path and brings it back to the ground. Gravity is so familiar, so constant, so woven into your everyday experience that you barely think about it. It's just there. It's always been there. And on Earth, it feels manageable. You can jump. You can climb stairs. You can lift heavy objects if you're strong enough. Earth's gravity doesn't feel oppressive. It feels normal because your body evolved to function in exactly this amount of gravitational pull. Every muscle, every bone, every organ in your body is calibrated to Earth's gravity. But here's what most people don't think about. The gravity you feel on Earth is specific to Earth. It's determined by Earth's mass and Earth's size. If you were on a different world with a different mass, gravity would feel completely different. On the moon, you'd feel light, bouncing with every step. On Mars, you weigh barely a third of what you weigh on Earth. These are worlds where gravity is gentler. But now imagine going in the other direction. Imagine a world where gravity is dramatically stronger. That's Jupiter. Jupiter's surface gravity, measured at the top of its cloud layers since there's no actual surface to stand on, is about 2.5 times stronger than Earth's. That means if you weigh 180 pounds on Earth, you weigh about 450 pounds at Jupiter's cloud tops. Think about what that means for your body. You'd feel like you were carrying another full-grown adult on your back at all times. Standing up would be exhausting. Walking would be grueling. Your heart would have to work much harder to pump blood against this increased gravitational pull. Your spine would compress. Your joints would ache. Even breathing would feel heavier because the muscles that expand your chest would be working against a stronger downward force. The human body simply isn't built for it. But this is just the beginning of Jupiter's gravitational story. Because the real problem isn't how heavy you'd feel standing at the cloud tops. The real problem is what it takes to leave. To understand why Jupiter is so hard to escape, you need to understand a concept called escape velocity. This is one of the most important ideas in all of space travel. Escape velocity is the speed you need to reach in order to break free from a celestial body's gravitational pull without any further propulsion. It's the speed at which your kinetic energy, the energy of your motion, is exactly enough to overcome the gravitational energy holding you down. Below that speed, gravity wins. You slow down, you fall back. At or above that speed, you win. You keep going outward, getting farther and farther away, with gravity weakening as you go, but never quite pulling you all the way back. On Earth, escape velocity is about 25,000 miles per hour. That's roughly 7 miles per second. To put that in perspective, a bullet fired from a high-powered rifle travels at about 1,700 miles per hour. Escape velocity from Earth is nearly 15 times faster than a bullet. It's about 33 times the speed of sound at sea level. When NASA launches rockets into space, they don't actually need to reach escape velocity all at once. Rockets burn fuel continuously, accelerating gradually, but the energy they need to expend is directly related to escape velocity. The higher the escape velocity, the more energy you need, the more fuel you need, the bigger the rocket has to be. This is why getting off Earth is so expensive and so difficult. Even with our most powerful rockets, we can only send relatively small payloads beyond Earth's gravity. The Saturn V rocket, which sent Apollo astronauts to the moon, was 363 feet tall and weighed 6.5 million pounds fully fueled. All of that mass, all of that engineering, all of that explosive energy contained in its engines was needed to send a tiny capsule weighing about 13,000 pounds to the moon and back. The ratio of the rocket's total weight to the payload weight is staggering. You need hundreds of tons of rocket to move a few tons of cargo beyond Earth's gravity. This is called the tyranny of the rocket equation, and it's one of the fundamental challenges of spaceflight. Every kilogram of fuel you add to the rocket adds weight, which means you need more fuel to lift that fuel, which adds more weight, which means you need even more fuel. It's a vicious cycle that makes space travel incredibly inefficient. On Earth, we've managed to overcome this challenge. We build enormous rockets, burn enormous amounts of fuel, and we can escape Earth's gravitational pull. It's expensive. It's difficult. It requires some of the most sophisticated engineering humanity has ever produced. But we can do it. We've done it hundreds of times. We've sent people to the moon. We've sent probes to every planet in the solar system. We've even sent spacecraft beyond the solar system entirely. Escaping Earth's gravity is hard, but it's achievable. Now let's talk about Jupiter. Jupiter's escape velocity is about 134,000 miles per hour. Let me say that again because the number is important. 134,000 miles per hour. That is roughly 5 times Earth's escape velocity. 5 times. On Earth, we need a Saturn V-sized rocket to reach escape velocity. On Jupiter, you'd need to go 5 times faster. And the energy required to reach a given speed doesn't scale linearly. It scales with the square of the velocity. This means that reaching 5 times the speed requires not 5 times the energy, but 25 times the energy. 25 times. To escape Jupiter's gravity, you would need roughly 25 times more energy per kilogram of payload than you need to escape Earth. Think about what that means in practical terms. The Saturn V was one of the most powerful machines ever built by humanity. It generated 7.5 million pounds of thrust at liftoff. It consumed fuel at a rate of about 15 tons per second during its first stage burn. And it was designed to escape Earth's gravity, not Jupiter's. To escape Jupiter, you would need a rocket that produces vastly more energy. And you'd need to carry all that fuel with you, which adds weight, which means you need even more fuel. The rocket equation becomes absolutely savage at Jupiter's escape velocity. The amount of fuel you'd need grows exponentially. For a chemical rocket, the kind we currently use, escaping Jupiter from its cloud tops would require a fuel-to-payload ratio so extreme that it borders on the absurd. You'd need thousands of tons of fuel for every kilogram of useful payload. The rocket would have to be almost entirely fuel with only a tiny fraction dedicated to the actual spacecraft. But let's step back for a moment and ask why Jupiter's gravity is so strong. What makes it so different from Earth? The answer comes down to mass. Jupiter is massive. Not just big, massive. There's an important distinction between size and mass in physics. Size is how much space something takes up. Mass is how much matter it contains. Jupiter is both large and massive, but it's the mass that determines gravitational pull. Jupiter has a mass of about 1.9 times 10 to the 27th kilograms. That's roughly 318 times the mass of Earth. If you took every other planet in the solar system, Mercury, Venus, Earth, Mars, Saturn, Uranus, and Neptune, and combined all their masses together, Jupiter would still be about 2.5 times heavier than all of them put together. Jupiter contains more mass than everything else in the solar system combined, excluding the Sun. It's the undisputed king of the planets. The Sun contains about 99.86% of the total mass in our solar system. Of what remains, Jupiter contains most of it. Every other planet, moon, asteroid, and comet combined is less massive than Jupiter alone. This enormous mass creates an enormous gravitational field. Newton's law of universal gravitation tells us that the gravitational force between two objects depends on their masses and the distance between them. The more massive an object is, the stronger its gravitational pull. Jupiter is 318 times more massive than Earth. If Jupiter were the same size as Earth, its surface gravity would be 318 times stronger. But Jupiter is also much larger than Earth. It has a diameter of about 86,881 miles, roughly 11 times Earth's diameter. This larger size means the cloud tops where you'd measure surface gravity are farther from Jupiter's center, and gravity weakens with distance. The farther you are from the center of a massive object, the weaker the gravitational pull. So Jupiter's enormous size partially offsets its enormous mass. The cloud tops are far enough from the center that the gravity there is only about 2.5 times Earth's, not 318 times, but escape velocity depends on both mass and radius in a different way. It depends on the total gravitational energy you need to overcome to leave the planet entirely. And because Jupiter has so much more mass than Earth, even though it's also much larger, the total gravitational energy binding you to Jupiter is immense. That's why escape velocity is 5 times higher than Earth's. The gravity at the cloud tops is only 2.5 times stronger. But the total depth of the gravitational well, the total amount of energy needed to climb completely out, is enormous because you have to fight Jupiter's massive gravitational pull all the way out. Let me explain what a gravitational well is, because this concept is crucial to understanding why Jupiter is so difficult to escape. Imagine a rubber sheet stretched tight like a trampoline. Now place a bowling ball on it. The bowling ball creates a dip, a depression in the sheet. The heavier the bowling ball, the deeper the dip. This is an analogy for how mass warps space. In general relativity, Einstein showed that mass warps space-time. Massive objects create dips in the fabric of space-time, and other objects fall into these dips. That's what gravity is. It's not really a force pulling you down, it's the shape of space-time guiding your motion. The deeper the dip, the harder it is to climb out. Earth creates a modest dip in space-time. It's deep enough to hold onto an atmosphere and keep the moon in orbit, but shallow enough that a well-built rocket can climb out of it. Jupiter creates a much deeper dip. Much, much deeper. If you could visualize the gravitational wells of the planets in our solar system, Earth's well would look like a gentle depression. Jupiter's well would look like a deep pit. And to escape from a planet means climbing from the bottom of that pit all the way back up to flat ground, to the point where the planet's gravity no longer has a meaningful hold on you. The deeper the pit, the more energy you need to climb out. Here's a useful way to think about it. When you launch a rocket from Earth, that rocket is climbing out of Earth's gravitational well. It's trading chemical energy stored in its fuel for gravitational potential energy, height above the planet. Every meter it rises, it gains a little more potential energy. When it's used enough energy to reach the top of Earth's gravitational well, it's free. It can coast away without falling back. On Jupiter, the well is so much deeper that reaching the top requires enormously more energy. It's like comparing climbing out of a ditch to climbing out of the Grand Canyon. Both involve going up, but the energy required is vastly different. Now, let's make this even more concrete by looking at what actual spacecraft have done near Jupiter. Every mission we've ever sent to Jupiter has been designed to fly past it or orbit it, not to land on it and leave. And even orbiting Jupiter requires careful planning. The Juno spacecraft, which arrived at Jupiter in 2016, entered orbit by firing its main engine for 35 minutes to slow down enough to be captured by Jupiter's gravity. That 35-minute burn was one of the most critical moments of the entire mission. If the engine had failed, Juno would have flown past Jupiter and never returned. The amount of fuel Juno carried for this burn was carefully calculated. It had to be enough to slow the spacecraft down by just the right amount. Not too much, which would have put it in too low an orbit where Jupiter's radiation would destroy it. Not too little, which would have let it escape. Juno needed to thread a needle, and the size of that needle was determined by Jupiter's gravitational field. And here's the thing, Juno never had to escape Jupiter. It was designed to orbit and eventually be destroyed by plunging into Jupiter's atmosphere at the end of its mission. Getting away from Jupiter would have required even more fuel than getting captured by it. The Galileo spacecraft, which orbited Jupiter from 1995 to 2003, carried an atmospheric probe. This probe was released from Galileo and plunged into Jupiter's atmosphere in December of 1995. It transmitted data for about 57 minutes before the heat and pressure destroyed it. The probe descended to a depth where the pressure was about 23 times Earth's atmospheric pressure at sea level. At that depth, the temperature had risen to about 307 degrees Fahrenheit. And then the probe went silent, crushed and melted by conditions that were still relatively mild compared to what lies deeper inside Jupiter. That probe was never designed to come back. It was designed to die. Because bringing something back from inside Jupiter's atmosphere is a completely different problem than dropping something in. Dropping something into Jupiter is easy. Jupiter's gravity does all the work. You just let go, and gravity pulls the object down into the atmosphere. No fuel required, no propulsion needed. But bringing something back out means fighting against that gravity. It means converting all the potential energy you lost on the way down back into kinetic energy on the way up. And you need a way to generate that energy while surrounded by an increasingly hostile environment. Consider the numbers. The Galileo probe entered Jupiter's atmosphere at a speed of about 106,000 miles per hour. That's how fast it was going when it hit the cloud tops, accelerated by Jupiter's gravity during its descent from orbit. All of that kinetic energy was converted into heat by friction with the atmosphere. The probe's heat shield experienced temperatures of about 28,000 degrees Fahrenheit, briefly hotter than the surface of the sun. The deceleration forces reached 230 times Earth's gravity, 230 Gs. A fighter pilot blacks out at about 9 Gs. The probe experienced more than 25 times that. Now, imagine trying to do that in reverse. Instead of decelerating as you enter, you need to accelerate as you leave. You need to reach speeds of 134,000 miles per hour, going upward while fighting through a thickening atmosphere and ever-increasing gravity. The engineering challenges are beyond anything we've ever attempted. There's another important factor that makes Jupiter's gravitational well particularly treacherous, and that's the concept of delta V. In spaceflight, delta V is the total change in velocity that a spacecraft can achieve. It's determined by the exhaust velocity of the engine and the ratio of fuel mass to total mass. Every maneuver in space, every orbit change, every landing, every takeoff costs delta V. And delta V is finite. You can only carry so much fuel, and each kilogram of fuel only provides so much change in velocity. For a mission to Jupiter, the delta V budget is enormous. Just getting from Earth to Jupiter requires a significant amount of delta V. Entering Jupiter's orbit requires more, and escaping from Jupiter's atmosphere, if you were deep inside it, would require a delta V that dwarfs anything we can currently achieve with chemical rockets. The Juno spacecraft had a total delta V budget of about 1,800 miles per hour for its entire mission. Escaping from Jupiter's cloud tops would require roughly 134,000 miles per hour. That's more than 70 times Juno's entire fuel capacity. Even the most efficient chemical rockets can't carry enough fuel to generate this kind of delta V while also carrying useful payload. This is why every Jupiter mission we've ever flown has been a one-way trip into the system. We send spacecraft there, but we never bring them back. They orbit until their fuel runs out or their instruments degrade, and then they either crash into Jupiter or drift away on an uncontrolled orbit. Bringing something back from Jupiter orbit is theoretically possible, but would require enormous amounts of fuel. Bringing something back from inside Jupiter's atmosphere is, for all practical purposes, beyond our current technological capability. Let me put Jupiter's gravity in one more perspective by comparing it to the other planets. Mercury has an escape velocity of about 9,600 miles per hour. Venus is about 23,000 miles per hour. Earth is about 25,000 miles per hour. Mars is about 11,200 miles per hour. Saturn is about 79,300 miles per hour. Uranus is about 47,600 miles per hour. Neptune is about 52,700 miles per hour. And Jupiter, 134,000 miles per hour. It's not even close. Jupiter's escape velocity is nearly 70% higher than Saturn's, the second highest. Jupiter stands alone among the planets as the most gravitationally dominant world in our solar system. And remember, escape velocity is measured from the cloud tops, from the outermost layer of Jupiter's atmosphere. If you're deeper inside the planet, the escape velocity from that depth would be different. In some ways, as you go deeper toward Jupiter's core, the gravity you experience actually changes in complex ways because there's more mass above you, partially cancelling the pull from below. But the energy required to climb out of the gravitational well from a deeper point is always greater because you have more distance to climb through an increasingly dense atmosphere. You're not just fighting gravity at that point. You're fighting gravity and atmospheric resistance simultaneously. It's like trying to swim upward from the bottom of an ocean that gets thicker and heavier the deeper you go. This brings us to something important. Jupiter's gravity alone makes escape extraordinarily difficult. Even from the cloud tops, even in the best case scenario where you're at the very top of the atmosphere with nothing but space above you, you still need to reach a speed of 134,000 miles per hour to break free. That's a staggering requirement, one that pushes our engineering to its absolute limits. With current rocket technology, escaping from Jupiter's cloud tops would be theoretically possible, but would require a rocket far larger and more powerful than anything we've ever built. The fuel requirements would be immense, the engineering challenges would be formidable, but it's at least within the realm of physics. You can do the math and get an answer that's not infinity. It's enormous, but it's finite. From higher up, from orbit around Jupiter, escape becomes easier. Spacecraft in high orbits around Jupiter can use relatively modest burns to escape, especially if they use gravitational assist from Jupiter's moons. This is how we've sent spacecraft like Voyager and New Horizons beyond the outer solar system by using Jupiter's gravity as a slingshot rather than a trap. But here's where the real terror of Jupiter begins, because gravity is only the first problem. If Jupiter were a rocky world with a solid surface, we could at least imagine building a launch facility on that surface. We could imagine constructing a rocket, fueling it, and launching it upward into the sky. The escape velocity would still be enormous, but the problem would at least be familiar. It would be like launching from Earth, just much harder. But Jupiter isn't a rocky world. Jupiter doesn't have a solid surface. Jupiter is something fundamentally different from any world humans have ever experienced. And that difference transforms the escape problem from merely extremely difficult to something that borders on the physically impossible. Because on Jupiter, there's nowhere to stand. There's nowhere to build. There's nowhere to launch from. There's only atmosphere, getting thicker and denser and hotter the deeper you go, with no bottom in sight. And this changes everything about how you'd need to think about escape. This isn't just a harder version of launching from Earth. This is an entirely different kind of problem, one that our engineering has never been designed to solve. And understanding why requires us to go deeper into Jupiter, literally deeper, into the atmosphere itself, into the layers of gas and pressure and heat that make Jupiter not just a planet but a prison, with no walls and no floor, only an endless suffocating grip that tightens the further you fall. When you think about a planet, you probably imagine something like Earth. A solid ball of rock with mountains and valleys and oceans. A surface you can stand on. A ground beneath your feet. Even when you think about other worlds, you picture them this way. Mars has deserts and canyons and polar ice caps. You could stand on Mars. You could walk across it. You could drive a rover across its surface, and in fact, we've done exactly that. Venus has a surface, a brutally hot one covered in volcanic plains, but a surface nonetheless. The Soviet Venera landers touched down on Venus in the 1970s and 80s, sat on solid ground, took photographs, and transmitted data before the heat and pressure destroyed them. Mercury has a surface cratered and baked, but solid. Even the moons of the outer solar system have surfaces. Europa has an icy crust. Titan has a surface so cold that water ice behaves like rock and liquid methane fills its lakes. Everywhere we've explored in the solar system, we've found surfaces. Solid ground. A place where down ends and something holds you up. Jupiter is different. Jupiter doesn't have a surface. Not in any way that would be useful. Not in any way that resembles what you picture when you hear the word ground. Jupiter is a gas giant, and that name, gas giant, is one of those scientific terms that sounds descriptive but actually undersells the strangeness of what it describes. When most people hear gas giant, they imagine a big ball of gas, like a balloon but planet-sized. Maybe they imagine something hollow inside, or something with a small rocky core at the center surrounded by a thick atmosphere. And while that last part isn't entirely wrong, the reality is far more alien than any simple description can convey. Jupiter is not a planet with a thick atmosphere. Jupiter is atmosphere, almost entirely. From the cloud tops all the way down toward the center, there's no clean boundary between atmosphere and planet. There is no moment where gas ends and solid begins. Instead, there is a continuous gradient, a slow, relentless transition from thin gas at the top to something unimaginably dense and hot at the bottom. And this gradient is what makes Jupiter so fundamentally different from any rocky world. On Earth, the atmosphere is a relatively thin shell. If Earth were the size of a basketball, the atmosphere would be thinner than a coat of paint on that basketball. You can drive to the edge of the atmosphere. Commercial airplanes fly at about 35,000 feet, which is already in the upper atmosphere. The boundary between atmosphere and space is generally placed at the Kármán line, about 62 miles above sea level. That's it. 62 miles of gas, and then you're in space. Below the atmosphere is rock. Solid, dependable rock. Thousands of miles of it, all the way down to the iron core at the center. There's a clear division. Up there is air. Down here is ground. You always know which side you're on. Jupiter has no such division. The atmosphere at the cloud tops is thin by Jupiter standards, but already denser than you might expect. As you descend, the gas gets thicker. Not suddenly, not in discrete layers, continuously. Imagine sinking into an ocean, but instead of there being a surface of the ocean, a clear line between air and water, the air just gradually becomes water. At some point, you're not in air anymore, but you can't point to the exact moment it changed. That's what descending into Jupiter is like, except instead of air becoming water, hydrogen gas becomes something far more exotic. Let's walk through what would actually happen if you descended into Jupiter's atmosphere. This isn't hypothetical in the abstract sense. We have real data from the Galileo atmospheric probe, which entered Jupiter's atmosphere on December 7th, 1995. And we have detailed models built from decades of observation and physics. So this is grounded in real science. You enter from the top. The outermost layers of Jupiter's atmosphere are made mostly of hydrogen and helium, the two lightest elements in the universe. At the very top, where the atmosphere fades into the vacuum of space, the gas is incredibly thin. If you were floating here, you'd barely notice the atmosphere. It would feel almost like space, but you're falling. Jupiter's gravity is pulling you down at 2.5 times the rate you'd fall on Earth, and as you fall, the atmosphere thickens. The first recognizable features you'd encounter are the cloud tops. Jupiter's visible surface, the colorful bands and swirls you see in photographs, is actually the top of a cloud layer at a pressure of about 1 atmosphere, roughly the same as sea level pressure on Earth. These clouds are made of ammonia ice crystals. They're cold, about minus 230 degrees Fahrenheit at the cloud tops. The colors come from complex chemical reactions driven by sunlight and lightning. The exact chemistry is still debated, but trace amounts of sulfur, phosphorus, and organic compounds are likely responsible for the reds, oranges, and browns you see in Jupiter's bands. Below the ammonia clouds, at a depth where pressure reaches about 2 atmospheres, roughly twice Earth's sea level pressure, there's a layer of ammonium hydrosulfide clouds. These are brownish, and they exist in a region where the temperature has warmed to about minus 50 degrees Fahrenheit. Still cold, but warming rapidly. Deeper still, at about 5 atmospheres of pressure, you reach water clouds. These are similar to the clouds on Earth, made of water droplets and ice crystals. The temperature here is roughly 80 degrees Fahrenheit. Room temperature. For a brief moment, in this narrow band of Jupiter's atmosphere, the temperature and pressure are actually not that different from Earth's surface. If you could somehow float at this depth, the air pressure would feel like being about 130 feet underwater. Uncomfortable, dangerous, but not instantly fatal. Scuba divers have survived pressures like this, though not for long and not without careful decompression. But this narrow band of almost familiar conditions is fleeting. You're still falling. And below the water clouds, everything changes rapidly. As you continue descending, the pressure increases relentlessly. At 10 atmospheres, 10 times Earth's sea level pressure, you're in a region where the temperature is climbing past several hundred degrees. There are no more clouds. The gas around you is clear but dense. You can feel it resisting your movement, like moving through thick air that's becoming more like a fluid with every passing moment. At 100 atmospheres, equivalent to the pressure nearly 3,300 feet beneath Earth's ocean surface, the temperature has risen to about several hundred degrees Fahrenheit. The hydrogen and helium gas around you is now dense enough to feel like a thick fog. Not quite liquid, not quite gas. It's somewhere in between, and it's getting denser all the time. At 1,000 atmospheres, a pressure that would crush a military submarine into a crumpled ball of metal, the temperature has exceeded 1,000 degrees Fahrenheit. The gas around you is now so dense that it behaves more like a fluid. The distinction between gas and liquid has become blurry. In fact, at these conditions, hydrogen enters what's called a supercritical state. A supercritical fluid is something that exists beyond the critical point of a substance, the temperature and pressure at which the distinction between liquid and gas ceases to exist. Below the critical point, you can clearly tell whether something is a gas or a liquid. Above it, you can't. The substance has properties of both. It fills its container like a gas, but it's dense like a liquid. It can dissolve things like a liquid, but it diffuses like a gas. For hydrogen, the critical point occurs at about minus 401 degrees Fahrenheit and about 13 atmospheres of pressure. Jupiter exceeds these conditions within the first few hundred miles of atmosphere. So, for most of Jupiter's interior, the hydrogen isn't really a gas or a liquid in the traditional sense. It's a supercritical fluid, a state of matter that has no everyday equivalent in human experience. This is crucial to understanding why Jupiter has no surface. On a rocky planet, there's a clear phase boundary. You have gas atmosphere above and solid or liquid surface below. The transition is sharp. On Earth, you can stand at the beach and point to the exact line where air meets water. You can stand on a mountain and feel the solid rock beneath your feet and the gas atmosphere above your head. These boundaries exist because the materials are different. Rock is rock, air is air, water is water. They have different compositions and different properties, and they meet at defined interfaces. On Jupiter, there's no such boundary. The atmosphere is made of hydrogen and helium. The deeper interior is also made of hydrogen and helium. The same stuff. There's no compositional change to create a surface. And because the hydrogen transitions through a supercritical state, there's no phase change either. The gas just gets denser and denser and denser, smoothly and continuously, until it's denser than any liquid you've ever encountered, and then it keeps getting denser. There's no splash, no impact, no moment of landing. You never arrive because there's nowhere to arrive at. You just keep sinking into thicker and thicker material, pressed ever deeper by gravity, with the temperature and pressure climbing steadily the whole time. This lack of a surface fundamentally changes the nature of the escape problem. On Earth, if you want to escape the planet's gravity, you start from the surface. You build a launch pad on solid ground. You construct a rocket in a factory, transport it to the pad, fuel it, and launch it. The ground gives you something to push against. Newton's third law says that for every action, there is an equal and opposite reaction. A rocket engine pushes exhaust gases downward, and the reaction force pushes the rocket upward. But the rocket also needs to be stationary before launch. It needs to be sitting on something solid, held in place while the engines build up thrust, and then release to fly upward. This entire process depends on having a surface. On Jupiter, there's no surface. So where do you launch from? The answer is you don't launch in any traditional sense. There's no pad. There's no ground to anchor to. There's no facility to build. No infrastructure to support a launch operation. If you somehow had a spacecraft inside Jupiter's atmosphere, it would need to maintain its own altitude through continuous thrust or buoyancy. It can't just sit somewhere and wait. It will be perpetually sinking unless it actively fought against gravity at every moment. This means that before you even begin the escape attempt, before you even start accelerating upward toward escape velocity, you're already spending energy just to stay in place. On Earth, a rocket sitting on the launch pad doesn't need to burn fuel to avoid sinking into the ground. The ground holds it up for free. On Jupiter, there's no free support. Gravity is pulling you down constantly, and there's nothing solid to resist it. You either burn fuel to hover, or you sink. And if you sink, conditions get worse. The deeper you go, the higher the pressure, the higher the temperature, the denser the atmosphere. Every meter you sink makes escape harder. Let me try an analogy. Imagine you're treading water in the middle of the ocean. There's no land in sight, no boat, no flotation device. You're using your own energy to stay at the surface. Now imagine someone tells you that you need to fly. You need to launch yourself upward out of the water, accelerate to an incredible speed, and keep going until you reach space. But you can't touch the bottom because the ocean is miles deep. You can't stand on anything. You have to generate all your upward velocity while treading water, while already exhausting yourself, just staying afloat. This is a crude analogy for what escaping Jupiter would be like. Except, the ocean is made of hydrogen that gets progressively thicker, and the gravity pulling you down is 2.5 times stronger than what you're used to. And instead of getting colder as you sink deeper, it gets hotter. Much, much hotter. And the pressure doesn't just increase the way it does in an ocean. It increases far beyond anything any ocean on Earth could produce. There's another problem created by the lack of a surface, and it has to do with how we build things. Every piece of engineering humanity has ever created was built on solid ground. Our factories are on the ground. Our materials are stored on the ground. Our tools operate on the ground. Even our spacecraft are assembled in buildings that sit on the ground. The entire infrastructure of spaceflight depends on having a stable, solid platform from which to work. None of this is possible inside Jupiter's atmosphere. You can't build a factory in a place that has no floor, store materials where everything sinks, or perform precision engineering where temperatures and pressures are constantly increasing and winds howl at hundreds of miles per hour. This means that any vehicle intended to escape from Jupiter would have to be brought from outside. You'd have to build it elsewhere, fly it to Jupiter, and then somehow deploy it within the atmosphere. But here's the problem with that approach. Any vehicle you send into Jupiter's atmosphere has to survive entry. And surviving entry into Jupiter is extraordinarily difficult. As we discussed, the Galileo probe endured 28,000 degree temperatures and 230 Gs during entry. It survived, descended for 57 minutes, and was destroyed at a depth of about 97 miles and 23 atmospheres of pressure. It was never meant to come back. A vehicle designed to enter Jupiter's atmosphere and then escape again would face the entry conditions, survive them, descend into the atmosphere, somehow stabilize, and then generate enough energy to accelerate back upward through the atmosphere it just descended through, fighting gravity and atmospheric drag the entire way, reaching a speed of 134,000 miles per hour before breaking free into space. The engineering requirements are beyond anything we can currently imagine. Now, let's talk about wind. Because Jupiter's atmosphere isn't just thick and hot and crushing, it's also incredibly dynamic. Jupiter has the most powerful atmospheric dynamics of any planet in the solar system. The bands you see in photographs of Jupiter are actually alternating jet streams. The light-colored bands are called zones. The dark-colored bands are called belts. Zones are regions of rising gas. Belts are regions of sinking gas. The boundaries between these bands are where the most extreme winds occur. Wind speeds in Jupiter's atmosphere can exceed 300 miles per hour. Some jet streams near the equator reach speeds of over 400 miles per hour. To put that in perspective, the most powerful hurricanes on Earth, Category 5 storms, have sustained winds of about 157 miles per hour or higher. Jupiter's regular atmospheric winds are more than twice as fast as the most extreme weather Earth can produce. And these aren't occasional storms, they're permanent features. Jupiter's banded structure has been observed for hundreds of years. The winds never stop, they never calm down. They blow continuously, driven by Jupiter's rapid rotation and intense internal heat. Jupiter rotates once every 9 hours and 56 minutes. That might seem unremarkable until you consider Jupiter's size. Earth rotates once every 24 hours. Jupiter's equator is about 11 times larger, yet it completes a rotation in less than 10 hours. This means Jupiter's equator is spinning at about 28,000 miles per hour, compared to Earth's 1,000 miles per hour. This rapid rotation generates enormous Coriolis forces, the same effect that causes hurricanes on Earth to spin, and these forces drive Jupiter's powerful jet streams and banded wind patterns. For anything inside Jupiter's atmosphere, these winds are a constant threat. A spacecraft trying to maintain position would be battered by winds that shift direction across bands. Moving between bands could expose you to wind shear, sudden changes in wind speed and direction that could tear a vehicle apart. On Earth, wind shear is one of the greatest dangers to aircraft. Pilots are trained to avoid it. On Jupiter, wind shear is everywhere, all the time, at speeds that would destroy any aircraft ever built on Earth. The Great Red Spot is perhaps the most famous atmospheric feature on Jupiter. It's a massive anticyclonic storm, meaning it rotates opposite to the surrounding flow, like a giant eddy in a river. The Great Red Spot has been observed continuously since at least the 1800s, and it might have existed for much longer. At its peak size, the Great Red Spot was large enough to fit about 3 Earths across its width. Even today, after decades of gradual shrinking, it's still about 1.3 times Earth diameter. The winds at the edge of the Great Red Spot reach about 270 miles per hour. Inside the storm, conditions are even more extreme. Recent observations from the Juno spacecraft have revealed that the Great Red Spot extends to a depth of at least 200 miles below the cloud tops, and possibly much deeper. It's not a shallow surface feature, it's a deep atmospheric structure, a column of churning gas extending far into Jupiter's interior. Imagine being caught in this storm, not from above, looking down at it from the safety of orbit, but inside it, surrounded by it, winds of 270 miles per hour tearing at you from every direction, the gas around you thickening as you descend, temperature climbing, pressure building, no ground below you, no sky above you that you can reach without generating enormous amounts of energy. Just the storm, endless and ancient and powerful beyond anything on Earth. And the Great Red Spot is just one storm. Jupiter has many others. The Juno spacecraft has discovered massive cyclones at Jupiter's poles, arranged in geometric patterns. The North Pole has a central cyclone surrounded by 8 smaller cyclones arranged in an octagonal pattern. The South Pole has a central cyclone surrounded by 5 others in a pentagonal arrangement. Each of these polar cyclones is larger than the entire continental United States. These storms are believed to extend deep into the atmosphere, powered by Jupiter's internal heat and rapid rotation. They appear to be stable long-term features, not temporary weather events. Jupiter's entire atmosphere is a machine of immense power, driven by forces on a scale that has no comparison on Earth. All of this matters because any attempt to escape Jupiter must contend not only with gravity and the lack of a surface, but also with these atmospheric dynamics. You can't simply point your vehicle upward and accelerate. You'd be fighting crosswinds of hundreds of miles per hour. You'd be battling turbulence on a scale that makes the worst thunderstorms on Earth seem gentle. You'd be navigating through layers of atmosphere that change in density, temperature, and wind direction as you ascend. And you'd be doing all of this while trying to accelerate to 134,000 miles per hour relative to Jupiter's center of mass. Let me bring this back to the fundamental problem. On Earth, escaping gravity is a matter of engineering. You build a powerful enough rocket, you carry enough fuel, and you launch from a solid surface into a thin atmosphere that offers only modest resistance. The atmosphere is an inconvenience, not a barrier. Rockets punch through Earth's atmosphere in minutes. Most of the drag occurs in the lowest few miles. After that, the air thins rapidly and drag becomes negligible. On Jupiter, the atmosphere is the planet. There's no punching through it. There's no getting above it in a few minutes. The atmosphere extends for tens of thousands of miles. The deeper you are, the denser it becomes. Drag. The resistance the atmosphere exerts on a moving object increases with the density of the fluid and the square of the object's speed. As you try to accelerate upward through Jupiter's atmosphere, drag increases enormously. You need to go fast to escape, but going fast through a dense atmosphere creates enormous drag, and drag converts your kinetic energy into heat. The faster you go, the more heat your vehicle generates. At the speeds required for escape, the heating would be extreme, potentially destroying any vehicle before it could reach the upper atmosphere. This is the opposite of the entry problem. When the Galileo probe entered Jupiter's atmosphere, it was moving fast, and the atmosphere slowed it down. The kinetic energy was converted to heat, and the heat shield absorbed it. For escape, you need to move fast through a dense atmosphere, generating the same kind of heating, but in reverse. Except now you need to survive it while also maintaining thrust and accelerating. The Galileo probe's heat shield was designed for one-time use. It ablated away, sacrificing itself to protect the probe. An escaping vehicle would need heat protection that works continuously during a sustained upward climb, not just a brief entry pulse. The engineering for this simply doesn't exist. There's one more aspect of Jupiter's atmosphere that makes the escape problem worse, and it's the sheer depth. Jupiter's atmosphere doesn't extend for 62 miles like Earth's. From the cloud tops to the center of Jupiter, the distance is roughly 43,000 miles. That's more than 5 times the diameter of Earth. The atmosphere just keeps going, and the deeper you go, the worse everything gets. The pressure doubles roughly every few hundred miles. The temperature climbs steadily. The density increases. The transition from gas to supercritical fluid happens gradually. And then, deeper still, something even stranger occurs. But we'll come to that. For now, the key point is this. Jupiter has no surface. It has no ground. It has no floor. It is a world made entirely of atmosphere that gets progressively denser and hotter as you descend, with no boundary, no stopping point, no place where you can say here is the bottom. And this means that any object inside Jupiter is suspended in a fluid, held up only by whatever force it can generate against gravity. The moment that force fails, the moment your engines stop or your fuel runs out, you sink. And sinking means moving to a region of higher pressure and higher temperature, which makes everything harder. Your engines have to work against denser fluid. Your structure has to withstand greater pressure. Your heat shields have to endure higher temperatures. Every failure cascades. A small loss of thrust leads to sinking, which leads to higher pressure, which leads to greater structural stress, which leads to further loss of capability, which leads to further sinking. It's a death spiral, literally. A downward spiral into conditions that no machine can survive. On Earth, if a rocket engine fails during launch, the rocket falls back to the ground. It crashes. It's destroyed on impact. But the destruction happens because of the sudden stop at the surface. Without an engine, a rocket in Earth's atmosphere falls for maybe a minute before it hits the ground. On Jupiter, there is no ground to hit. If your engine fails, you don't crash. You sink. Slowly at first, then faster as you pick up speed, and you keep sinking. There's no impact to end it quickly. Instead, the atmosphere just gets thicker and hotter and denser around you. Your vehicle is gradually crushed and cooked. The process might take hours. It would be a slow, relentless destruction. Not a sudden crash, but a progressive tightening of the environment around you until nothing can withstand the conditions. And during this entire time, you're conscious, aware, able to observe your own descent into conditions that grow worse with every passing minute. There's something uniquely terrifying about that. A crash is sudden. It's over in an instant. Being slowly squeezed and heated by an atmosphere that has no bottom is something else entirely. It's not a collision. It's an absorption. Jupiter doesn't smash things. It absorbs them. It takes them in, wraps them in ever-increasing pressure and heat, and slowly dismantles them at the molecular level. This is the world you need to escape from. Not a world with mountains and oceans and launch pads. A world without any solid feature at all. A world where the very concept of a surface doesn't apply. A world made of gas that gradually becomes liquid, that gradually becomes something else entirely. A world that pulls you in with 2.5 times Earth's gravity and offers you absolutely nothing to push against, nothing to stand on, nothing to anchor to, just atmosphere. Infinite seeming, ever-thickening atmosphere. And somewhere deep down inside all that gas, where the pressure reaches millions of times Earth's atmospheric pressure, and the temperature climbs to tens of thousands of degrees, something truly alien awaits. Something that makes the supercritical hydrogen above it seem almost ordinary. The deeper interior of Jupiter holds conditions so extreme that they don't exist anywhere else in our solar system outside of the Sun itself. And understanding those conditions is essential to understanding why escaping from any significant depth inside Jupiter transitions from extraordinarily difficult to genuinely impossible. So far, we've talked about Jupiter's gravity and the fact that Jupiter has no solid surface. Both of these alone make escape extraordinarily difficult, but now we need to go deeper, literally deeper, because the true horror of Jupiter isn't at the cloud tops. It isn't in the first few 100 miles of atmosphere where conditions are merely brutal. The true horror lies thousands of miles below, in regions where the laws of chemistry and material science as we understand them reach their absolute limits and then break. Where matter itself is forced into states so exotic that they barely exist anywhere else in the known universe. Where the pressures and temperatures are so extreme that no material ever engineered by human hands could survive for even a fraction of a second. This is the deep interior of Jupiter, and understanding what happens down there is essential to understanding why escaping from any significant depth inside this planet isn't just difficult. It's a physical impossibility with any technology we can currently imagine or even theoretically design. Let's start by establishing a frame of reference. On Earth, the atmospheric pressure at sea level is about 14.7 pounds per square inch. That's defined as 1 atmosphere. It's the pressure you're experiencing right now as you sit and listen to this. You don't notice it because your body is perfectly adapted to it. Your lungs, your blood vessels, your eardrums, everything is calibrated to function at 1 atmosphere. When you dive underwater, pressure increases by 1 atmosphere for every 33 feet of depth. Recreational scuba divers rarely go below 130 feet, about 5 atmospheres. The deepest a human has ever dived is about 1,090 feet, roughly 34 atmospheres, a descent that took 12 minutes but required 15 hours of decompression to return safely. That gives you a sense of how even modest pressures become dangerous. The deepest point in Earth's ocean is the Challenger Deep in the Mariana Trench, about 36,000 feet below the surface. The pressure there is approximately 1,086 atmospheres. Only a handful of submersibles have ever visited this depth. The vehicles that made it were specially designed pressure vessels with thick walls made of titanium and advanced composites, engineered to withstand the crushing force of the deep ocean. Even these purpose-built machines operated at the very edge of material capability. A tiny flaw in the hull, a microscopic crack, a poorly sealed viewport, any of these could cause catastrophic implosion. The water pressure at the bottom of the Mariana Trench would crush an unprotected human body instantly. It would collapse a submarine not designed for those depths like crumpling an aluminum can. 1,086 atmospheres is an extreme pressure by any standard on Earth. It represents the absolute deepest point on our planet, the most extreme pressure environment Earth's ocean can offer. Keep that number in your mind. 1,086 atmospheres, because we're going to leave it far behind. Inside Jupiter, pressure increases rapidly with depth. At the cloud tops, the pressure is about 1 atmosphere, similar to Earth's surface. By the time you've descended about 200 miles below the cloud tops, the pressure has reached about 100 atmospheres. That's equivalent to being about 3,300 feet beneath Earth's ocean surface, already far beyond what any conventional submarine could survive. The temperature at this depth is approaching several hundred degrees Fahrenheit. The hydrogen around you is no longer a gas in any recognizable sense. It's a supercritical fluid, dense and hot. By about 600 miles below the cloud tops, the pressure has climbed to roughly 1,000 atmospheres, essentially matching the bottom of Earth's deepest ocean. And you've barely begun your descent into Jupiter. You're still in what scientists consider the upper atmosphere. The real interior hasn't even started yet. At roughly 1,200 miles below the cloud tops, the pressure reaches about 10,000 atmospheres, 10 times the deepest ocean on Earth. No human-made submersible has been designed to operate at this pressure. Our best deep-sea vehicles operate at about 1,000 atmospheres, and even those represent the pinnacle of pressure vessel engineering. 10,000 atmospheres is simply beyond our experience. Materials that are considered strong on Earth begin to behave differently at these pressures. Steel would deform, titanium would compress. Even diamond, one of the hardest materials known, begins to behave in unusual ways under pressures of this magnitude. But we're still not even close to the extremes Jupiter has to offer. Keep descending. At about 3,000 miles below the cloud tops, the pressure reaches approximately 100,000 atmospheres. 100,000. That is 100 times the pressure at the bottom of the Mariana Trench. The temperature at this depth is somewhere around 3,600 degrees Fahrenheit. Hotter than the melting point of steel. Hotter than the melting point of iron. Hot enough to melt virtually any metal used in engineering. The hydrogen at this depth is incredibly dense. It's no longer anything you would recognize as a gas. It's a thick, hot, supercritical fluid that resists movement. Pushing through it would be like trying to push through molten metal, except the pressure is far higher than anything you'd experience in a foundry or a blast furnace. And still, we haven't reached the most extreme conditions, not by a long way. At about 12,000 to 13,000 miles below the cloud tops, something remarkable happens. The pressure reaches approximately 2 million atmospheres. 2 million. That number is so far beyond anything in human experience that it's difficult to even find meaningful comparisons. 2 million atmospheres is about 2,000 times the pressure at the bottom of Earth's deepest ocean. It's already more than half the pressure found at the very center of the Earth. Reached here while still thousands of miles from Jupiter's own center, At this pressure and at temperatures exceeding 9,000 degrees Fahrenheit, hydrogen undergoes a fundamental transformation. It becomes metallic. Metallic hydrogen. This is one of the most extraordinary substances in the known universe. To understand what metallic hydrogen is, you need to understand a little bit about how atoms behave under extreme pressure. Under normal conditions, hydrogen is the simplest element in the universe. Each atom consists of one proton and one electron. Hydrogen molecules are made of two hydrogen atoms bonded together, sharing their electrons. In its gaseous form, hydrogen is light, transparent, and an electrical insulator. It doesn't conduct electricity because its electrons are tightly bound to individual molecules. They're not free to move around and carry electrical current. But when you squeeze hydrogen hard enough, when you apply pressures of millions of atmospheres, the molecules are forced so close together that their electron orbitals begin to overlap. The electrons are no longer bound to individual molecules. They become delocalized, free to move throughout the material. This is exactly what happens in metals like copper and iron. The electrons form a sea of mobile charges that can carry electrical current. Under these extreme conditions, hydrogen transforms from an insulating gas into a metallic liquid. It conducts electricity. It reflects light. It behaves like a liquid metal, similar in some ways to mercury, except far denser and far hotter. This isn't theoretical speculation. Metallic hydrogen has been predicted by physicists since 1935, when Eugene Wigner and Hilliard Bell Huntington first proposed that hydrogen would become metallic under sufficient pressure. Since then, scientists have been trying to create metallic hydrogen in laboratories on Earth. This is extraordinarily difficult because the pressures required are so enormous. The primary tool for creating these pressures is the diamond anvil cell, a device that uses two opposing diamonds to squeeze a tiny sample between their tips. Diamonds are used because they're the hardest known natural material and can withstand enormous pressures before failing. In 2017, a team at Harvard led by Isaac Silveira claimed to have produced metallic hydrogen in a diamond anvil cell at a pressure of about 495 gigapascals, which is roughly 4.9 million atmospheres. The claim was controversial because the diamond broke before the sample could be fully characterized, and other labs have had difficulty reproducing the result. But even the pressures achieved in these experiments are in the range of what exists inside Jupiter. The fact that we need the hardest material on Earth pushed to its absolute breaking point to even briefly create the conditions that exist throughout a vast region of Jupiter's interior tells you something about the extremity of those conditions. Inside Jupiter, the metallic hydrogen layer is enormous. It extends from about 12,000 to 13,000 miles below the cloud tops all the way down to a possible core region, which might begin at roughly 25,000 to 30,000 miles below the cloud tops. This means the metallic hydrogen layer is roughly 12 to 18,000 miles thick. For perspective, the entire diameter of Earth is only about 7,926 miles. Jupiter's metallic hydrogen layer is thicker than two entire Earths, stacked on top of each other. And this layer isn't some exotic curiosity found in a thin band deep inside the planet. It makes up the majority of Jupiter's interior by volume. Most of Jupiter, by volume, is metallic hydrogen. The gas and supercritical fluid layers that we've been discussing, the layers that contain the cloud tops and the visible features, are actually a relatively thin skin over a vast ocean of liquid metal. When you look at Jupiter through a telescope, when you see those beautiful bands and that iconic great red spot, you're seeing just the outermost fraction of the planet. Beneath that thin visible layer lies something alien and immense. A world-sized ocean of liquid metallic hydrogen, conducting electricity, generating magnetic fields, and existing under pressures and temperatures that defy easy comprehension. The magnetic field is worth mentioning because it's a direct consequence of the metallic hydrogen layer. Jupiter has the most powerful magnetic field of any planet in the solar system. It's roughly 20,000 times stronger than Earth's magnetic field. This magnetic field is generated by currents flowing in the metallic hydrogen layer. As Jupiter rotates, the conducting metallic hydrogen moves, and those moving charges create electrical currents, which in turn generate a magnetic field. This is the same basic mechanism that generates Earth's magnetic field, except Earth's field is generated by currents in its liquid iron outer core. Jupiter's field is generated by currents in a much larger region of metallic hydrogen, which is why the resulting magnetic field is so much more powerful. Jupiter's magnetic field extends millions of miles into space. It creates a magnetosphere, a bubble of magnetic influence, that is the largest continuous structure in the solar system. If you could see Jupiter's magnetosphere with your eyes, it would appear several times larger than the full moon in Earth's sky. That's how enormous it is. Charged particles trapped in this magnetosphere create intense radiation belts around Jupiter. These radiation belts are so powerful that they pose a severe hazard to spacecraft. The Juno spacecraft's electronics are housed inside a titanium radiation vault specifically designed to protect them from Jupiter's radiation. Even with this protection, Juno's instruments are gradually being degraded by the intense radiation environment. But let's return to the question of escape. Imagine you're somehow at the top of the metallic hydrogen layer, about 12 to 13,000 miles below the cloud tops. The pressure here is about 2 million atmospheres. The temperature exceeds 9,000 degrees Fahrenheit. You're surrounded by liquid metallic hydrogen, a substance denser than water, conducting electricity, existing under conditions that would obliterate any known material in an instant. What would it take to escape from this depth? Let's think about it. First, you would need a vehicle that could survive at 2 million atmospheres of pressure. No material known to science can do this. The strongest materials humans have ever created can withstand maybe a few 100,000 atmospheres under ideal laboratory conditions, and even then only in tiny samples for brief periods. A vehicle large enough to carry propulsion systems and fuel would need structural integrity across its entire surface at 2 million atmospheres. This is simply not possible with any known material. Carbon fiber, titanium, tungsten, diamond, none of them come close. The vehicle will be crushed flat, atomized really, in a tiny fraction of a second. Second, even if you somehow had an indestructible vehicle, you would need a propulsion system that operates at 9,000 degrees Fahrenheit. Most rocket engines operate by combusting fuel and generating hot exhaust gases. The hottest part of a typical rocket engine, the combustion chamber, reaches temperatures of about 5,000 to 6,000 degrees Fahrenheit. At 9,000 degrees, the ambient temperature outside the vehicle is already hotter than the inside of a rocket engine's combustion chamber. Your fuel would need to burn at temperatures higher than the surrounding environment to generate any thrust. Finding a fuel that can combust at temperatures significantly above 9,000 degrees is an enormous challenge. Most chemical fuels break down at temperatures well below this. Third, even with an indestructible vehicle and an impossibly high temperature engine, you would need to push through 12 to 13,000 miles of increasingly dense material to reach the cloud tops. You'd be accelerating upward through supercritical hydrogen that offers tremendous drag. The deeper you start, the denser the material, and the more energy you'd lose to drag. By the time you fought your way up through thousands of miles of this dense fluid, the fuel requirements would be astronomical in every sense of the word. Fourth, after fighting through all that material, you'd still need to reach an upward velocity of 134,000 miles per hour to actually escape Jupiter's gravitational well. And the atmosphere doesn't just let you go quietly. Even in the upper layers, drag is significant. You'd be losing energy to the atmosphere the entire way up, meaning you'd need to generate far more than 134,000 miles per hour worth of kinetic energy to account for the losses from atmospheric resistance. Each of these challenges alone is insurmountable with current or foreseeable technology. Combined, they make escape from the metallic hydrogen layer not just practically impossible, but physically absurd. It's like asking how you would walk to the sun. The question has no meaningful answer because the premise itself is beyond the bounds of possibility. Now, let's go even deeper, because Jupiter's interior holds one more secret. Below the metallic hydrogen layer, at the very center of the planet, there might be a core. The nature of Jupiter's core has been debated for decades. Early models suggested Jupiter might have a solid core of rock and ice about 10 to 20 times the mass of Earth. This core would have been the original seed around which Jupiter formed. In the early solar system, about 4.5 billion years ago, a rocky and icy body roughly 10 to 20 times Earth's mass formed in the outer solar system. This body's gravity was strong enough to begin attracting the hydrogen and helium gas that dominated the solar nebula. As more gas accumulated, the gravity increased, attracting even more gas. This runaway process continued until Jupiter had swept up a vast amount of hydrogen and helium, becoming the gas giant we see today. The original rocky and icy body would have become the core, buried under tens of thousands of miles of hydrogen. But the Juno spacecraft, which has been orbiting Jupiter since 2016, has provided data suggesting the core might not be a neat, well-defined solid ball. Instead, it appears the core might be diluted, meaning the heavy elements rock, metals and ices are mixed in with the surrounding hydrogen rather than being concentrated in a distinct layer. This dilute core might extend across a significant fraction of Jupiter's radius. The conditions at Jupiter's center are extreme beyond the already extreme conditions in the metallic hydrogen layer. Pressure at the core is estimated at roughly 30 to 40 million atmospheres. The temperature is estimated at approximately 35,000 to 45,000 degrees Fahrenheit. For comparison, the surface of the Sun is about 10,000 degrees Fahrenheit. Jupiter's core is 3 to 4 times hotter than the surface of the Sun. At these pressures and temperatures, matter behaves in ways that are genuinely alien. The rock and metal that might make up the core aren't solid. They can't be solid at these temperatures. They aren't liquid in any ordinary sense either. They exist in exotic high-pressure states that don't correspond to anything in everyday experience. The atoms are squeezed so close together that their electron shells overlap and merge. The material becomes a plasma-like fluid, a dense soup of nuclei and delocalized electrons where the normal rules of chemistry barely apply. No laboratory on Earth can replicate these conditions for more than tiny fractions of a second in minuscule volumes. The largest pressure experiments ever conducted, using diamond anvil cells and laser-driven shock compression, have reached pressures in the range of a few million atmospheres, and even then only for nanoseconds in samples smaller than a grain of sand. Jupiter sustains pressures 10 times higher than this across a region thousands of miles wide, continuously, and has done so for 4.5 billion years. The gulf between our laboratory capabilities and Jupiter's interior conditions is enormous. We can barely peek at these conditions in fleeting experiments. Jupiter exists in them permanently. Let's talk about what would happen to actual materials at these depths, because understanding material failure is crucial to understanding why escape is impossible. Consider steel. Structural steel, the kind used in buildings and bridges, has a yield strength of about 36,000 pounds per square inch. That means if you apply more than 36,000 pounds of force per square inch, the steel permanently deforms, it bends, it crumples. At 1 atmosphere of pressure, steel is incredibly strong by everyday standards. But 1 atmosphere is only 14.7 pounds per square inch. At 100 atmospheres, the external pressure on a steel structure is about 1,470 pounds per square inch. Steel can handle this. At 1,000 atmospheres, the pressure is about 14,700 pounds per square inch. Steel is starting to struggle. At about 2,500 atmospheres, the external pressure exceeds steel's yield strength. The steel deforms. The structure collapses. This happens at a depth of only about 50 miles inside Jupiter. 50 miles. Jupiter's radius is about 43,000 miles. At 50 miles below the cloud tops, you've penetrated barely 1/10% of the way to Jupiter's center, and steel has already failed. What about stronger materials? Titanium alloys have yield strengths up to about 180,000 pounds per square inch. They'd last a bit deeper, maybe to about 12,000 atmospheres. That extends your survival depth to perhaps a few hundred miles. Still a tiny fraction of Jupiter's radius. Tungsten, one of the strongest metals known, has a yield strength of about 150,000 pounds per square inch, but can be alloyed to withstand more. Carbon fiber composites can be incredibly strong in certain directions, but are vulnerable to uniform external pressure. Diamond is the hardest natural material, but is brittle. Under immense uniform pressure, it might survive to extreme depths, but it would eventually reach a point where the crystal structure itself deforms under the sheer load. The deepest conceivable survival depth for any engineered structure, using the absolute strongest materials available to modern science and pushing every engineering margin to its theoretical maximum, would be somewhere in the range of a few thousand miles, maybe 5,000 miles below the cloud tops, if we're being wildly optimistic. And at that depth, the structure wouldn't be functional. It would be a barely intact shell on the verge of collapse, certainly not capable of housing engines, fuel, guidance systems, and life support. A functioning spacecraft with the ability to generate thrust and navigate would fail at much shallower depths, probably within a few hundred miles of the cloud tops. And fuel itself becomes a problem at these depths. Rocket fuel needs to be stored, managed, and combusted in a controlled way. The fuel tanks need to maintain structural integrity. The pumps that feed fuel to the engines need to function. The combustion chamber needs to contain the explosion of burning fuel and direct the exhaust in a controlled direction. All of this machinery is made of materials, metals, ceramics, seals, valves, electronics that have operational limits. Temperatures above a few thousand degrees destroy most materials used in rocket engines. Jupiter's atmosphere exceeds these temperatures within a few thousand miles of the cloud tops. Even if the structure of your vehicle somehow survived the pressure, the heat would cook your engines and your fuel. Liquid hydrogen, which is used as rocket fuel, and which conveniently is also the main component of Jupiter's atmosphere, boils at about minus 423 degrees Fahrenheit at 1 atmosphere. At the temperatures found hundreds of miles inside Jupiter, hydrogen isn't just boiling. It's a supercritical fluid at temperatures of thousands of degrees. Using it as fuel becomes a completely different chemical and thermodynamic challenge compared to burning cryogenic hydrogen in the cold vacuum of space. There's also the question of electronics. Every modern spacecraft depends on electronic systems for navigation, communication, engine control, and every other function. Electronics are built from semiconductors, typically silicon. Semiconductors work because they can switch between conducting and insulating states, which is the basis of transistors and all digital computing. But at temperatures above about 300 degrees Fahrenheit, standard silicon electronics begin to malfunction. At temperatures above about 600 degrees Fahrenheit, silicon semiconductors fail entirely. The thermal energy is enough to promote electrons across the band gap without any external signal, turning the semiconductor into a conductor and making it useless for computation. Specialized high-temperature electronics exist, built from materials like silicon carbide or gallium nitride, that can operate at temperatures up to about 1,000 degrees Fahrenheit. But even these reach their limits well below the temperatures found a few thousand miles inside Jupiter. Without functioning electronics, a spacecraft cannot navigate. It cannot control its engines. It cannot communicate. It becomes a blind, deaf, helpless shell falling through an ocean of fire and pressure. The Galileo probe, specifically hardened against pressure and heat, lasted less than an hour before its electronics failed at only 97 miles deep and 23 atmospheres. Conditions that were, by Jupiter's standards, still relatively mild. The probe barely scratched the surface of Jupiter's atmosphere and it was destroyed. The conditions that destroyed it exist within the first 1% of Jupiter's radius. The remaining 99% is far, far worse. When you put all of this together, a picture emerges that is profoundly humbling. Jupiter's interior is a place where human engineering reaches its absolute limits almost immediately. Within the first 100 miles, conditions exceed anything we've ever built a machine to withstand for extended periods. Within the first few 100 miles, conditions exceed the theoretical limits of most known materials. Within a few thousand miles, conditions enter a regime where matter itself is forced into exotic states that we can barely replicate in laboratories. And at the center, conditions rival those found inside small stars, pressures of tens of millions of atmospheres and temperatures hotter than the surface of the sun. No material, no engine, no electronic system, no fuel, nothing in the entire catalogue of human technology can function at these depths. And escaping from these depths means not only surviving in conditions that destroy everything, but also generating enough energy to propel yourself upward through tens of thousands of miles of increasingly dense material against the most powerful planetary gravitational field in the solar system. The energy requirements are beyond enormous. They're beyond anything we can achieve with chemical propulsion. They're beyond anything we can achieve with nuclear propulsion. They might be beyond anything achievable with any propulsion technology consistent with known physics. At a certain depth inside Jupiter, escape doesn't just become difficult, it becomes meaningless as a concept. The conditions are so far beyond the survival threshold of any possible machine that talking about escape is like talking about swimming through solid granite. The idea itself breaks down because the preconditions for the attempt can't be met. You can't escape if you can't survive. And you can't survive in the deep interior of Jupiter. Nothing can. Nothing made of ordinary matter operating under the laws of physics as we understand them can maintain structural integrity, generate thrust, and navigate at pressures of millions of atmospheres and temperatures of tens of thousands of degrees. Jupiter's deep interior is, for all practical and theoretical purposes, a one-way destination. Things go in, nothing comes out. And the thing about Jupiter is that it's always pulling you in that direction. Deeper. Always deeper. Now we need to bring everything together. Because the full picture of why Jupiter is so extraordinarily difficult to escape isn't captured by any single factor alone. It's not just the gravity, it's not just the lack of a surface, it's not just the crushing pressure or the extreme heat or the exotic states of matter deep in the interior. It's the combination of all of these things working together, layered on top of each other, each one making every other one worse. Jupiter doesn't present a single obstacle to escape. It presents an interlocking system of obstacles, each reinforcing the others, creating a trap that tightens with every meter of depth. And understanding how these factors combine is what transforms Jupiter from merely a difficult place to leave into something that approaches a physical impossibility for anything caught deep enough inside it. Let's start by thinking about what escape actually requires, not in the abstract, but in concrete physical terms. To escape from any point inside Jupiter, you need three things simultaneously. First, you need a vehicle that can survive at that depth. It needs to maintain structural integrity against the pressure. It needs to resist the temperature. It needs to protect its internal systems, its fuel, its engines, its guidance electronics from the environment. Second, you need a propulsion system that can generate enough thrust at that depth to overcome gravity and atmospheric drag and accelerate upward. This propulsion system needs fuel, and that fuel needs to be stored and delivered to the engines under the ambient conditions. Third, you need enough total energy to climb all the way out of Jupiter's gravitational well from whatever depth you're at, fighting through an atmosphere that gets thinner as you ascend, but that started enormously dense, while maintaining enough velocity to eventually reach escape speed at the cloud tops and beyond. All three of these requirements must be met simultaneously. Failing any one of them means you don't escape. And the critical insight about Jupiter is that as you go deeper, all three requirements become harder to meet at the same time. Not just linearly harder, but exponentially harder. The difficulty doesn't increase gradually, it explodes. Consider what happens at the cloud tops, the highest point of Jupiter's atmosphere where pressure is roughly 1 atmosphere. At this altitude, the survival requirement is relatively manageable. 1 atmosphere of pressure is what we experience on Earth's surface. The temperature is cold, about minus 230 degrees Fahrenheit, which is challenging but within the range of spacecraft thermal management systems. We've built probes that operate in cold environments. The main challenge at the cloud tops is propulsion. You need to reach 134,000 miles per hour. That's an enormous velocity, roughly 5 times Earth's escape velocity. With chemical rockets, achieving this from the cloud tops would require a truly massive vehicle, almost entirely composed of fuel. The rocket equation is merciless. For a chemical rocket with a specific impulse of about 450 seconds, which represents the best hydrogen and oxygen engines we've built, the fuel-to-payload ratio needed to reach Jupiter's escape velocity would be staggering. You'd need roughly several hundred tons of fuel for every ton of useful payload. That's not impossible in principle. It's extreme, but it's within the realm of physics. You can write down the equations and get a finite answer. A vehicle the size of a skyscraper, almost entirely fuel, could theoretically launch a small capsule to escape velocity from Jupiter's cloud tops. It would be the most ambitious engineering project in human history by orders of magnitude, but the physics allows it. The atmosphere at this altitude is thin enough that drag, while significant, doesn't make escape fundamentally impossible. You'd lose energy to atmospheric resistance during the ascent, which means you'd need even more fuel to compensate. But again, the problem has a solution in principle. Now drop down just a few hundred miles. The pressure has increased to several hundred atmospheres. The temperature has risen to over 1,000 degrees Fahrenheit. The atmosphere is now a thick, supercritical fluid. Suddenly, all 3 requirements have become dramatically harder. Survival requires a pressure vessel capable of withstanding hundreds of atmospheres, which is achievable with current materials, but adds enormous weight to the vehicle. That additional structural weight means you need more fuel to lift it. More fuel means more weight. More weight means an even larger pressure vessel. The rocket equation spiral tightens viciously. The propulsion system now has to operate in a dense, hot environment. The engine exhaust needs to push against a surrounding fluid that's hundreds of times denser than air at sea level. Thrust is reduced because the exhaust can't expand as efficiently in a dense medium. Think about the difference between blowing air in an empty room versus blowing air underwater. The denser the medium, the harder it is to generate propulsive force by expelling exhaust. Your engines become less efficient precisely when you need them to be more efficient. And the total energy requirement has increased because you're starting from a deeper point in the gravitational well. You need to climb an additional few hundred miles through dense atmosphere just to reach the cloud tops. And then you still need to reach escape velocity from there. The fuel budget grows enormously. Not just because you need more delta V, but because you're carrying more structural mass to survive the pressure, and because your engines are less efficient in the denser atmosphere. Each factor multiplies the others. This is the fundamental trap. At a few hundred miles deep, escape is still theoretically possible, but would require a vehicle so massive and so technologically advanced that it's far beyond anything humanity has ever built or seriously designed. The payload you could actually deliver to escape velocity from this depth would be vanishingly small compared to the total vehicle mass. Go deeper, 1,000 miles below the cloud tops. Pressure is now in the thousands of atmospheres. Temperature is several thousand degrees Fahrenheit. The hydrogen around you is a dense, supercritical fluid, approaching the density of water. At this depth, the survival requirement alone becomes nearly impossible. No pressure vessel we can currently build would survive thousands of atmospheres while maintaining enough internal volume to house a propulsion system. The structural mass required to resist the external pressure would be so great that the vehicle would be almost entirely whole, with barely any room left for fuel or engines. The temperature exceeds the operational limits of most rocket engine materials. Combustion chambers are typically cooled by circulating fuel around them, using the cold fuel as a heat sink. But if the ambient temperature outside the vehicle is already several thousand degrees, the fuel isn't cold anymore. It's been heated by the environment before it even reaches the engine. The thermal management problem becomes circular. You need cool fuel to cool the engine, but the fuel is hot because the environment is hot. You need to cool the fuel before you can use it to cool the engine. But cooling requires energy. And energy requires fuel. Everything feeds back on itself. The propulsion challenge at this depth is equally severe. You're trying to push exhaust through a fluid that's nearly as dense as liquid water. The drag on your ascending vehicle would be enormous. At the speeds you'd need to achieve for escape, the drag forces would exceed what any known propulsion system could overcome. It's not just about having enough thrust. It's about having enough thrust to overcome both gravity and the wall of dense fluid above you that resists your upward motion. Chemical rockets simply cannot do this. Their thrust-to-weight ratios are insufficient for climbing through a fluid this dense, while also carrying the fuel needed for the full ascent. You need something dramatically more powerful. Nuclear thermal propulsion offers better specific impulse, meaning more thrust per unit of fuel. A nuclear thermal rocket heats hydrogen to extreme temperatures using a nuclear reactor, then expels it as exhaust. The specific impulse of a nuclear thermal engine is roughly twice that of the best chemical engines. This helps. It roughly halves the fuel ratio needed. But it doesn't solve the problem because the fuel requirements at this depth are so astronomical that halving them still leaves you with impossible numbers. And a nuclear reactor adds mass, complexity, and radiation hazards to a vehicle already struggling under the weight of its own pressure hull. What about nuclear pulse propulsion? This is the concept behind Project Orion, studied in the 1950s and 60s. The idea is to detonate small nuclear bombs behind a spacecraft and ride the shockwaves. It sounds insane, but the physics actually works. Nuclear pulse propulsion offers specific impulses of 10,000 seconds or more, roughly 20 times better than chemical rockets. With this kind of efficiency, the fuel ratio for escaping Jupiter improves dramatically. But you're detonating nuclear bombs inside a dense, fluid atmosphere. The shockwaves would interact with the surrounding hydrogen in complex and violent ways. The detonations would generate temperatures of millions of degrees in their immediate vicinity, creating plasma fireballs that would expand against the surrounding high-pressure fluid. The structural loads on the pusher plate, the massive metal plate at the back of the spacecraft that absorbs the nuclear shockwaves, would be enormous, far greater than in the vacuum of space where Orion was originally designed to operate. And you still need a vehicle that survives at thousands of atmospheres of ambient pressure while carrying a stockpile of nuclear devices and maintaining the structural integrity of a pusher plate being repeatedly hammered by nuclear detonations. The engineering challenges are so far beyond our capability that it's essentially science fiction. At 3,000 miles deep, we reach the point where meaningful discussion of escape essentially ends. The pressure is around 100,000 atmospheres. The temperature is around 3,600 degrees Fahrenheit. No known material can maintain structural integrity under these conditions while also serving as a functional vehicle. The strongest alloys deform and flow like putty at these pressures. The hottest tolerant ceramics soften and fail. Diamond, if you could somehow build a vehicle from it, might survive the pressure for a time, but diamond oxidizes, which means it burns in the presence of oxygen. And while Jupiter's atmosphere is predominantly hydrogen, the temperatures are so extreme that chemical reactions become unpredictable. More importantly, even if you had a perfectly indestructible vehicle, the propulsion problem remains unsolvable. No engine design currently known or theoretically proposed can generate enough thrust at these conditions to lift a meaningful payload upward through tens of thousands of miles of dense fluid against Jupiter's gravity. The energy requirements don't just grow with depth, they grow with depth while the efficiency of every propulsion system decreases with depth. You need more energy precisely when you have less ability to generate it. This is the death spiral I mentioned earlier, but applied to the physics of propulsion rather than the physics of sinking. Every factor gets worse simultaneously, and each worsening factor makes every other factor worse. Let me try to make this more vivid. Imagine you're in a swimming pool. At 12 feet deep, you push off the bottom and surface in seconds. Easy. At 100 feet, you need training and slow decompression. At 1,000 feet, you need a submersible and hours of careful ascent. At 100,000 feet, deeper than any ocean on Earth, every submarine ever built will be crushed. It's beyond our engineering. And here's the crucial part. Jupiter's equivalent isn't a pool of water. It's a pool of hydrogen that's being compressed by the gravity of a planet 318 times more massive than Earth. The pool isn't 100,000 feet deep. It's equivalent to tens of millions of feet deep. And the fluid isn't just water. It transitions from gas to supercritical fluid to liquid metal as you descend. At every stage, the resistance to upward motion increases. The energy needed to ascend increases. And the conditions become more hostile to any technology you might use for the ascent. The swimming pool analogy breaks down long before we reach Jupiter's actual conditions, because nothing in human experience is comparable. There's a concept in physics called the point of no return. In the context of black holes, this is the event horizon, the boundary beyond which nothing, not even light, can escape. Jupiter doesn't have an event horizon. Jupiter isn't a black hole. Light can escape from Jupiter at any depth. Electromagnetic radiation has no mass and travels at the speed of light. So Jupiter's gravity can't trap it the way a black hole can. But for physical objects, for anything made of matter with mass and structural limits and finite energy, Jupiter has something functionally similar to a point of no return. It's not a sharp boundary, it's a gradient, a gradual transition from difficult to impossible. At the cloud tops, escape is theoretically possible with sufficient technology. A few hundred miles down, it's theoretically possible, but requires technology far beyond our current capability. A few thousand miles down, it's theoretically possible only with speculative propulsion systems that may never be built. And somewhere in the range of several thousand to 10,000 miles below the cloud tops, escape transitions from extraordinarily difficult to genuinely impossible for any vehicle made of ordinary matter, regardless of what propulsion system it uses. Not because the physics of propulsion fails in some abstract theoretical sense, but because no material can survive the conditions long enough to use any propulsion system. This is the key distinction. For a black hole, The impossibility of escape is fundamental. It's built into the geometry of space-time. Nothing can escape from within the event horizon, not because of engineering limitations, but because all paths through space-time point inward. Jupiter's impossibility is different. It's a practical impossibility rather than a fundamental one. In principle, the physics allows escape from any point inside Jupiter. There's no law of physics that says matter can't move upward inside Jupiter, but the conditions required to survive and generate thrust are so extreme that no real machine can meet them. It's like saying that, in principle, you could walk from New York to London. There's no law of physics preventing it. But the Atlantic Ocean is in the way, and you can't walk on water, so in practice, it's impossible by that method. Jupiter's deep interior is an ocean of physics that prevents escape by any practical method. Now, let me address something important. I've been talking about escape from deep within Jupiter as being impossible, and I want to be precise about what I mean. When I say impossible, I don't mean that some future civilization with unimaginably advanced technology couldn't conceivably find a way. I mean that with any technology consistent with our current understanding of physics and material science, escape from deep inside Jupiter cannot be achieved. If someone invented a material that could withstand millions of atmospheres of pressure and tens of thousands of degrees of temperature, and if they invented a propulsion system that could generate enormous thrust in a medium denser than liquid mercury, then perhaps escape would become feasible. But such materials and systems don't exist, and there's no clear path to creating them. They would require breakthroughs in physics and engineering so fundamental that we can't even specify what those breakthroughs would look like. It's not like we know what we need and just haven't built it yet. We don't even know if what we would need can exist. From higher altitudes, the picture is less absolute but still daunting. From the upper atmosphere, within the first 100 miles or so, escape is theoretically possible with technology that's extremely advanced, but not physically impossible. A vehicle with sufficient fuel, powerful engines, and robust thermal protection could potentially ascend through the upper atmosphere and achieve escape velocity. This would require a spacecraft far more capable than anything we've ever built, but it doesn't violate any known laws of physics. The Galileo probe survived for 57 minutes in the upper atmosphere before being destroyed. A vehicle designed for escape rather than descent, carrying propulsion systems and fuel, could potentially do what the Galileo probe could not. It could fight its way back up, but it would need to be enormous. The fuel requirements, even from the upper atmosphere, would make it one of the largest vehicles ever conceived, and it would face challenges we've never engineered solutions for. Sustained flight through a thickening atmosphere with increasing drag, thermal management during a prolonged high-speed ascent through hot dense gas, navigation and control in an environment with violent winds and turbulence, structural integrity under rapidly changing pressure conditions as it climbs from high pressure to low pressure. Each of these is a serious engineering problem, and they'd all need to be solved simultaneously. No mission has ever attempted a return from within Jupiter's atmosphere, because the engineering required is so far beyond our current capability. Even bringing a sample back from Jupiter's upper atmosphere, scooping up a tiny amount of gas and returning it to Earth, would be an enormously complex mission. The vehicle would need to enter Jupiter's atmosphere, collect a sample, and then have enough propulsion to escape back into orbit and return to Earth. The fuel requirements for this would be immense. The thermal and structural challenges would be severe. It's a mission that has been studied conceptually, but has never been seriously proposed because the technology doesn't exist. Compare this to the Moon, or even to Mars. We've brought samples back from the Moon. The Apollo astronauts landed on the lunar surface, collected rocks, and launched themselves back into lunar orbit using a small ascent stage. The Moon's escape velocity is only about 5,300 miles per hour. Its gravity is 1/6 of Earth's. There's no atmosphere to create drag. The ascent stage of the lunar module weighed about 10,300 pounds, including fuel. That was enough to reach lunar orbit from the surface. We've planned sample return missions from Mars as well. Mars's escape velocity is only about 11,200 miles per hour, and its atmosphere is about 1% of Earth's sea level pressure. The ascent vehicle can be small because the gravity is weak and the atmosphere offers little resistance. These missions are difficult and expensive, but they're within the realm of current engineering. Jupiter is categorically different. It's not just a harder version of the same problem. It's a different kind of problem entirely. On the Moon and Mars, you have a solid surface to launch from. You have weak gravity to overcome. You have thin or non-existent atmosphere to fight through. On Jupiter, you have no surface. You have the strongest planetary gravity in the solar system. You have an atmosphere so thick, it transitions into liquid and then into metallic fluid as you descend. The challenges aren't just greater in degree, they're different in kind. Let me put Jupiter's gravitational prison in broader perspective. In our solar system, Jupiter is the most difficult planet to escape from. We already looked at escape velocities across the solar system, and nothing comes close to Jupiter. Saturn is the next hardest planet to leave, but even Saturn's gravitational well is significantly shallower. The ice giants, Uranus and Neptune, are easier still, and the rocky planets with their thin or non-existent atmospheres and modest gravity are in an entirely different category. On those worlds, escaping is a solvable engineering problem. On Jupiter, it's something else entirely. Only the Sun has a deeper gravitational well than Jupiter. The Sun's escape velocity is about 1,381,000 miles per hour, roughly 10 times Jupiter's. But the Sun is a star, not a planet. Among the planets, Jupiter reigns supreme as the most gravitationally confining body in our solar system. Outside our solar system, there are worlds that might make even Jupiter look manageable. Hot Jupiters are gas giant exoplanets that orbit very close to their parent stars. Some are several times more massive than Jupiter, with correspondingly higher escape velocities and deeper gravitational wells. A planet 5 times Jupiter's mass would have an even more extreme interior, with higher pressures, higher temperatures, and an even thicker metallic hydrogen layer. Escaping from such a world would be even more impossible than escaping from Jupiter, if degrees of impossibility can even be meaningfully compared. There might also be super-Jupiters, objects on the boundary between planets and brown dwarfs, with masses 10 to 13 times Jupiter's. These objects would have interiors so extreme that they approach stellar conditions. Hydrogen fusion might even briefly ignite in their cores. Escaping from a super-Jupiter would be as unthinkable as escaping from the interior of a star. Jupiter, then, represents a kind of threshold. It's the most extreme planet in our solar system, the one with the deepest gravitational well and the most hostile interior conditions. It sits at the boundary between worlds you can theoretically interact with, and worlds that simply swallow you. You can land on Mars and leave. You can orbit Jupiter and leave. But entering Jupiter's atmosphere and leaving again requires a leap in technology so vast that it may never be bridged. And descending more than a few thousand miles into Jupiter means never leaving. Not because of some exotic physics or mysterious force, but because the pressure crushes you, the heat melts you, the gravity holds you, and the atmosphere smothers any attempt to generate the energy needed to climb back out. Jupiter has been capturing things for 4.5 billion years. Comets drawn in by its gravity have plunged into its atmosphere and been absorbed. Asteroids have followed the same path. In 1994, the world watched as Comet Shoemaker-Levy 9 broke apart and slammed into Jupiter's atmosphere in a series of impacts over 6 days. The fragments hit Jupiter at speeds of about 134,000 miles per hour, roughly Jupiter's escape velocity, which is not a coincidence. Objects falling into Jupiter from far away accelerate to approximately escape velocity by the time they hit the atmosphere. Each fragment explosion released energy equivalent to hundreds of thousands of megatons of TNT. The impact scars were visible for months. Dark spots larger than Earth mark the places where the comet fragments had been absorbed. But eventually those scars faded. Jupiter's atmosphere churned and mixed and smoothed over the wounds. The comet material, all those billions of tons of ice and dust and rock, was mixed into Jupiter's atmosphere and pulled down into the interior. It became part of Jupiter. It will never leave. Jupiter has been doing this since it formed. Everything that falls in stays. The planet grows slowly over time as it accumulates debris from the solar system. This is what Jupiter does. It collects, it gathers, it absorbs. Its gravity is a net that catches anything that comes too close. And once caught, the object descends into an atmosphere that gets denser and hotter without end, pressed ever deeper into conditions no material can withstand. There's something almost mythological about this. The ancient Romans named Jupiter after the king of the gods. They saw it as the brightest wandering star in the night sky after Venus, a commanding presence among the constellations. They couldn't have known that their intuition about Jupiter's dominance was physically accurate. Jupiter truly is the king of the planets. It dominates the solar system gravitationally. It influences the orbits of comets and asteroids. It may have played a crucial role in shaping the inner solar system, either shielding Earth from impacts or directing them toward us, depending on the time period. Its gravity has controlled the architecture of the outer solar system for billions of years. And its interior is a realm of such extreme physics that it resembles the inside of a failed star more than a planet in any familiar sense. When we look at Jupiter through a telescope, we see beauty. We see swirling bands of colour, amber and cream and rust. We see the great red spot, a storm older than most nations on Earth. We see a world that seems almost inviting in photographs, with its soft curves and warm hues, but that beauty is a mask. Beneath those cloud tops lies a descent into physics so extreme that it challenges our understanding of matter itself. A descent into pressures that crush steel like paper, temperatures that exceed the surface of the sun, and conditions that force hydrogen to become a liquid metal ocean thousands of miles deep. A descent that has no bottom in any meaningful sense, only a continuous tightening of the physical vice, a relentless increase in every parameter that makes survival impossible and escape unthinkable. Jupiter is not a world you can visit and leave. It's a world you can observe from a respectful distance, orbit if you're careful, perhaps Skim the upper atmosphere if you're very brave and very well equipped. But entering it with any intention of coming back is something that the laws of physics make functionally impossible beyond a relatively shallow depth. Not because we haven't tried hard enough, not because we need better rockets, but because the conditions inside Jupiter exceed the physical limits of any material, any engine, any technology that is consistent with our understanding of how matter and energy behave. Jupiter is the deepest gravitational well of any planet in our solar system. It has no surface to stand on. Its atmosphere extends for tens of thousands of miles, getting denser and hotter with every mile. Its interior reaches pressures of millions of atmospheres and temperatures of tens of thousands of degrees. And it has been this way for 4.5 billion years. Quietly, patiently, gathering everything that strays too close and pressing it down into conditions from which nothing returns. When you look up at Jupiter in the night sky tonight, you're seeing a bright point of light that looks peaceful and distant. But now you know what lies beneath that light. A world that doesn't just resist escape. A world whose physics makes escape from any meaningful depth structurally, thermally, and energetically impossible. Not the impossibility of something we haven't figured out yet. The impossibility of something the universe itself won't allow with ordinary matter under ordinary physics. Jupiter is beautiful from the outside, but from the inside, it is a prison with no walls, no floor, and no exit. Only an endless deepening of conditions that no technology can survive, and no engine can overcome. A planet that captures, compresses, and keeps everything that falls within its grasp. The physics that makes Jupiter impossible to escape isn't one thing, it's everything. Gravity, pressure, temperature, density, atmospheric depth, the absence of a surface, the failure of materials, the inadequacy of propulsion, the hostility of the environment to every system needed for survival and flight. All of these working together, reinforcing each other, creating a trap so thorough that it's not just hard to escape, it's hard to even imagine escaping. And that's what makes Jupiter unique among the worlds of our solar system. It's not just a big planet, it's a physical boundary, a threshold beyond which the familiar rules of exploration, of landing and launching and returning home, simply cease to apply. Jupiter is the planet that doesn't let go. And now you understand why. Let's start with something you already understand. Gravity. You feel it right now. It's holding you in your chair. It's keeping your feet on the floor. It's keeping the atmosphere wrapped around the Earth like a blanket. Every time you jump, gravity pulls you back down. Every time you throw a ball into the air, gravity curves its path and brings it back to the ground. Gravity is so familiar, so constant, so woven into your everyday experience that you barely think about it. It's just there. It's always been there. And on Earth, it feels manageable. You can jump. You can climb stairs. You can lift heavy objects if you're strong enough. Earth's gravity doesn't feel oppressive. It feels normal because your body evolved to function in exactly this amount of gravitational pull. Every muscle, every bone, every organ in your body is calibrated to Earth's gravity. But here's what most people don't think about. The gravity you feel on Earth is specific to Earth. It's determined by Earth's mass and Earth's size. If you were on a different world with a different mass, gravity would feel completely different. On the moon, you'd feel light, bouncing with every step. On Mars, you weigh barely a third of what you weigh on Earth. These are worlds where gravity is gentler. But now imagine going in the other direction. Imagine a world where gravity is dramatically stronger. That's Jupiter. Jupiter's surface gravity, measured at the top of its cloud layers since there's no actual surface to stand on, is about 2.5 times stronger than Earth's. That means if you weigh 180 pounds on Earth, you weigh about 400